Good morning. Let me first thank Christoph and the other people in his organizing team for this great conference, and especially also for the great dinner yesterday evening. That's quite amazing. So I will speak today about giving you more or less a high-level overview about what I have done together with Cédric Noël from the University of Lorraine in finite mixture modeling. The title is short and looks very easy. There is a little bit of a problem. I need to start explaining that, unfortunately, finite mixture modeling that refers to two different concepts in statistics, which is a little bit confusing sometimes. So for a lot of people, mixture modeling means working with mixtures of distributions. And there is this book called Finite Mixture Modeling from McLaughlin from 2000. That is not really what we are referring to, even if it's related. So there is another concept, another definition of a finite mixture model that comes from this book here from Daniel Nagin from Carnegie Mellon. And unfortunately, he used the same name for a model which is related to mixtures of distribution, but it's actually classification. And well, I checked Daniel yesterday on Google Scholars. He has 62,000 citations, so it seemed too big for us to change the name, so we just worked with his name. So obviously, this means that I will have to speak about what we really mean by finite mixture models. Then I will speak about the R package that Cédric has programmed. I will speak about extension of the model to underlying beta distribution, and I will not speak about the rest. So do not be afraid if you see 61 slides. I will not do all that today. The two others are papers in progress at of course. So, finite mixture model as we use it is actually cluster analysis. So we have a collection of trajectories, and we want to divide the population into groups, which are homogeneous, of course. And at the same time, the model estimates actually something like a typical trajectory for each subpopulation. So this is cluster analysis. It's actually, you can say it's fuzzy logic cluster analysis because it's not like k-means where each individual belongs exactly to one group. Here we'll have probability for each individual to belong to first group, second group, third group, and so on. Okay, so to go a little bit into the notations, we have our variable of interest y, which is time series. So we have n people in the sample. Well, individual, not necessarily people. We have t measures, which can be equidistant or not. And so the important thing to estimate here on top of this is the probability afterwards of a given subject to belong to a given group. We just need actually the typical conditions that for a given group, we suppose that conditional independence for the sequential realization of our y over the periods of measurement. Otherwise, we cannot do a mixture. And then we have the density of the function can be written as the sum actually over the k groups of the densities inside each groups. And so we can do this for different types of densities. I will tell you in a minute. So classically, already in Nagin's book, he works with Poisson distribution, binary logit distribution, normal distributions, which may be censored or not. And then in the papers that I, in a way, present today, we have extended this also to the beta distribution. So just to give you an example for one of the distribution, here's a normal distribution, what this is looking like. It's actually a maximum likelihood model. So the likelihood in the case of the normal distribution, you can see it here. It's not difficult, but it's too complicated to find closed form solutions for this. Nagin and his co-author Jones, they programmed in 2008 some test procedure, ProcTrush, which works nicely, but of course this test procedure is that's a black box, you cannot enter, you cannot change anything. And we needed some extensions to the model, so we needed to do it ourselves. I will explain a little bit later why. So first, there are two interesting extensions of the basic model. We can use covariates here. So first, we can use predictors of group membership, X, which should be taken before the time series, actually, if you want to use it in a causal way as predictors, of course. And then you have this little computational trick to write the group membership as a function of the predictors to be able to put it into the likelihood. It becomes a little bit more complicated, but still okay. And then the second idea is to add covariates to our model, which influence directly the trajectories in different groups. Unfortunately, so here was the starting point of my interest in these models was that in Nagin's model and also his software, of course, the influence of these trajectories were just on the intercept, which meant that if you have different values for your covariate, you just have parallel outcomes, which is not really good. And other things that I didn't like in his model is that he supposed that inside the different group, you always have this the same volatility, well, the same variance, which is also not very realistic in our kind of applications. So actually, the examples that we started working on were salary trajectories in Luxembourg. We had a project about the pension system, and for some insurance company who wanted to offer then supplementary private pension funds and so on depending on the different groups. For instance, here it's just a free salary group solution, but distinct for the covariate gender. So you have M is for men, W for women. You see that the trajectories are, of course, not parallel in real life. And since Nagin's model just allowed for parallel curves, we decided, or at that time it was myself, that we need something more general. So here is just for trajectories with their polynomials of order 4. And you see that what we want to do is to have not just our covariates having an influence on the intercept, but also in the other terms of the model. And then, of course, the other thing what I already said, that I want the error term to have a variance which is different for each group. So this is, of course, what I do not really go into the details. In all generalities, this is problematic, of course, can be problematic because it's now we are doing panel regressions, of course, and we need more hypotheses. This makes sense. So it's not even identified depending, so we need more conditions. In all generality, of course, this doesn't always work. That's obvious. So that's also statistical properties. Everything concerning the basic models like this, it's maximum likelihood if you have the usual, let's say, conditions, sample which is large enough, then it's obvious that these are consistent and there's some totally normal distributed in the normal case. It's not difficult to find the confidence intervals of your parameters and so on. For the rest, in our package for the moment, there's we didn't have time to do a lot of statistical tests for this supplementary test. So you can, of course, do your classical favorite test of work inside each group, but we haven't programmed a lot in this package yet. So will come later. Okay, so let's speak about this R package. I will, of course, not go into the details of the algorithms. It's already more than 40,000 lines, so Cedric did really an amazing job here. So just the function signature to speak a little bit about what's inside. So we have to resolve actually this maximum likelihood. There are two methods that are programmed. You can do the same as Nagin has done. Probably I never saw his code, it's a black box. But he says that he programmed by direct optimization of the likelihood functions. That is one possibility. The other possibility is we have programmed everything also with an EM algorithms. And since the two methods give the same results, that's also a good validation. I mean, I cannot guarantee that in these 40,000 lines of code there are no mistakes, obviously. So it's good to have two different methods and finding the same results at the end. Then the model is to give us a different distribution. So normally distributed or Poisson, and so on. And the others are more technical stuff where I do not go into the details because I do not have the time. The output you get always the numerical output, of course. For each group, you get your different parameters with standard errors and the usual test to see if it's significant. Then important always see is a two-group solution, so the size of the group, our PIs, and then we have a bunch of graphical results. So here is censored normal model. So you have the initial trajectories here colorized for the three groups, and then you see the lines as a typical trajectories per group, which here one is a constant and then the other two are polynomial function. And you can do the same things for the zero-inflated Poisson model, for the logit model. Plus something I didn't speak about. Actually, it's quite flexible. The user can also define other type of trajectories. So it's not a problem. The only thing, of course, is then you need to program your function yourself in R. So you need to be a little bit able to work in R. So for instance, here is a bunch of trajectories, and it didn't look really like a polynomial. So we tried to program, yeah, I have to. So this function for the trajectories depending on two parameters. The user then in R needs to define that function, of course, and then running our function in the model, it's NL for nonlinear general works fine too. So here we get the results. There's actually here still a mistake. I mean, it should not be intercept linear. It's the two parameters of the model, so K1 and K2. That I just saw that when I prepared the talk here, that there was in the numerical output, they always call actually the parameters as if it were polynomial. But model works, and you see also here for group solution, and that works fine. So some other things that we have inside the package to explore, to explain the different groups. You can have group profiles, so basically the averages of different other variables in the sample for each group. We have, of course, the membership's probabilities for all individuals. This is actually not parameters of the model with a few parameters that we have. So the parameters are just these PIs and then the trajectory parameters. The membership probabilities, individual ones, can be computed by a Bayesian procedure. I do not have a slide on this, but it's in the from the book of. Not too difficult. Then we have quite some possibilities to estimate the model performance, so average posterior probabilities, also of crack classification, and so on, that you can also get to see if your result makes sense or not. For model selection, for the moment, we have AIC, BIC programmed, and also slope heuristics, for those who know that. We are currently working also on another model selection criteria, but this paper, so for another day. Well, Cedric is very active, so there are all the time new features that appear. I'm not even exactly sure what the version that's now on CRAN, what is included and what is not yet, but it's always evolution. Okay, let me see. Yeah, I still have a little time. That's great. So what I actually wanted to really talk about today is our extension of the model now to underlying beta distribution. The beta distribution, well, I do not have to ask Christoph if it in his high quality, if it is considered a flexible distribution or not. But for us, at least it seemed much more flexible than just having normal. So the beta distribution is a 2-parameter distribution. Normal distribution is a special case, actually, but you can also have U-shaped densities. You can have, as you see here, you can have quite some different shapes of density. So it seemed quite interesting to us to extend the model also to data following beta distribution. For the beta distribution, the density is known and so on. So all we basically need is a linking function to the trajectories that we will have for each group, and that is given here on the slide. And then you get the likelihood of your data, and you have to program again the two methods to run the model. So that has been done. So this is integrated into the package, and I just show one example here. 2 years ago, the fancy data were COVID data, so it seemed a good idea to do that as an example, because everybody understands this data and know what we are speaking about. So we took COVID data from our World in Data, where you found data for all countries, well, 190 countries. And the main variable of interest here is the contamination rate, but it was just at the beginning. So it's data between January 2020 and April 2021. And then we had quite a lot of covariates here that we could use. So the typical ones that you find always in the news. So cases, population size, total case, the median age of population density, number of inhabitants, which are over 65. One which is of course important if you want to see if all these measures were efficient. There is some English colleagues have developed a government response stringency index to measure for different countries if they had a lot of measures or not. And then we used also GDP per capita, in poverty index, and some others. And here just if you're interested in the stringency index, it's actually 9 measures that have been used around the world that we used, that were used in England for this index. So things like school closures, work closure, cancellation of public event, and then forcing masks, closing everything, complete shutdowns, and so on. Okay, so just, the results of that. Here you see the 109 trajectories of the 190 countries that we then wanted to classify. I do not go into the details. For the model selection, we used Kaz and
Wassermann's criterion, which is based on BIC actually. So what we found then, different possibilities with number of groups and trajectories, and our solution was actually a 5-group solution where you have here trajectories in the correct colors, and then you have the typical 5 groups. If you are interested, actually colorizing the countries by colors, you see the 5 groups here on the screen, and on paper we have a little description of the groups. So you know all your favorite countries and know what happened, and so the results made basically sense. So what I want to speak a little bit about, so because here some interesting things happened when you used covariates. So for the predictors of group membership, this is a good illustration of causality or not causality. So from all the covariates that we tried as group membership predictors, there are only 2 that gave something interesting. So not surprisingly, of course, the median age of the population. Countries with older populations, they were in different groups than other countries. And then the interesting thing is about the stringency index, which was also, of course, significant. But that does not mean that the stringency index was a predictor of group membership. Actually, in these models, the predictor variable has to be measured before the beginning of the time series in order to be able to say that you have an influence or predictor. Here it was the contrary, of course. The stringency index was actually computed after or versus the end of our time series. So there is a relationship here. Okay, that is what statistics can prove, but there is definitely not a causal relationship. We argue in the paper that actually it's rather the other way around. It's the countries where you had a high contamination rate that had more measures, and so that influenced the stringency index, and not the other way around. And when we used it as covariates, time-dependent covariate, actually the result, I do not have time to go into the details of the results here, but they confirm actually that part of the analysis. So pedagogically, the message is as usual, causality is complicated and you need to be careful what you are doing. So just I said I would not have the time to go into the 2 other papers. At least just to come back to what I said initially, of course, these are not really mixture models in the sense of mixtures of distributions. So, of course, the result underlying is a mixture of distribution. For instance, here we created 5 groups of countries which different beta distributions underlying, and then we have a mixture. For all these 4 first papers, that didn't play a big role. So the only times that we really needed hardcore stochastic analysis to work with the mixture of distribution is actually for the identification of the models. There, that's really probability theory, and there it plays a role. Because, I mean, identifiability of this finite mixture model with included regression is not the same than just having the mixture of the distribution identifiable. Even in the very easy case of normal distributions, people actually for 40 years were writing that it was equivalent, and then Henning end of the 80s actually was the same, the first to prove that even for just simple linear regression, it was not the case, it's more complicated. So for a lot of results, it's of course, the results are partly coming from the mixture of distribution, partly from regression, but you need to include both and you get conditions which are more complicated than just what you need for identifying. Also have part coming from. Okay, so I was quite fast, but I started a little bit early too, but so I will finish here. Does it make sense to go into the details? The other two papers are more mathematical, and if I start, it will be